Hey guys. So here is like kind of like the next little part to 5.6. We technically haven't really covered the whole thing yet. We just kind of paused and did a project, but now we need to kind of take this a little bit deeper. Okay. So if you haven't watched the video that I posted just before this one, where I was talking about being able to kind of compare on Desmos. You'll see a screen like that. Compare on Desmos with the polar versus rectangular and seeing how those things correlate to each other, then please go and view that just so that some of this starts to click a little bit more for you. It's not very long, but I do want us to be able to kind of be on the same page. So if you haven't watched that yet, please go do that. Okay, so here we are. We are in our last little section actually for trigonometry. And we're going to wrap up polar coordinates here with this last little packet. So, okay, we're going to deal with rates of change. Now, if you guys remember rates of change, whenever you think of rate of change when it comes to like a linear function, we think of slope, right? And we have done like average rates of change in functions that are not linear. And we had a whole formula for that. So that's something we're going to get to. But before we do, we have to kind of talk a little bit about this like change in tandem and how these things correlate to each other. Specifically with talking about like the distance from it's just a little bit odd how they word this, but the radius always talks about like the distance from the center point, that origin, to where you are on the graph. So that's what R is always signifying, is that radius, or how far out from the center you're plotting that point. So what you're going to see here, first of all, and we're going to try to section this out because it kind of flip-flops a little bit. Okay, but this first thing that you're seeing on this is talking about in polar uh, in the polar form. So we have R equals f of theta. This is when your input is theta and your output is R. Okay, so right there, that's kind of what we're dealing with in this box that you're seeing. And there's a lot going on. Okay, I'm going to try to break it down the best I can, but it will hopefully start making more sense as we look through some of this. Okay, so we're talking about when we talk about where our R value is positive and increasing, or if it's negative and decreasing, then we're going to fit in this little category where it's saying that the distance between R and the origin is increasing. So what I want you to think about here is like as you start graphing this. Now, if you haven't watched the Desmos video, you need to go watch that so that you can remember how this works. But from the beginning of this function, we start graphing it right here. That's its little starting point, not at the origin. When it starts graphing, I want you to think about what's happening. Is this getting further away or closer to that origin? Well, that R value is getting more, so it's getting further away from the origin, right? So as that's happening, we get either your R is positive and increasing or it's negative and decreasing. So from the beginning, that happens. Now, once you turn, that distance from R to the origin starts to decrease, and it decreases until it hits the origin. That brings you into this category down here where it could be one of these two things. R is positive and decreasing, or R is negative and increasing. Once it hits that origin, it starts this little loop-de-loop, so it starts getting further away from the origin, and then it starts getting closer back to, and then it gets further away again, that little section right out there. So again, if you haven't watched that Desmos video, please go do that. I wish my program that we have to make these videos would let me go back and forth between the two things, but alas, it does not. So if I could go back and reference the Desmos thing real fast, I would, but I can't. So anyways, that's what I have here with in that little box. Is it's just trying to help you to straighten up your idea of when things are positive and increasing, negative and decreasing, and all that kind of stuff. And also talking about when your R, or the distance from the point to the origin, when that is increasing or decreasing. Now, that becomes a whole lot more clear in the capacity that we're used to seeing if we actually graph this rectangularly. So this is graphed on a polar grid, but what if you were to take the function and write it in rectangular coordinates and or a rectangular function of it? So that's what you're going to see down here. They've changed it to being, instead of being r and theta, we have f of x and we have x, right? Or y and x. So when we have it in that capacity, then we can see it show up in that wave pattern that we learned about from earlier on. As just a quick little idea, just to kind of keep your brain straight, this is talking about when your input is x and output is y. Okay, so we're switching gears and we're looking at this on a rectangular capacity instead of the polar. This is the exact same function. I don't know if you noticed that, but before we had 1 plus 2 sine theta. This is 1 plus 2 sine x. Same thing, it's just in rectangular format. We also still only have the our domain here, excuse me. The domain here is going from 0 to 2 pi, just like the other one had been. Okay, so what we're going to do here is try to answer this part where it's talking about our description. For those of y'all who are in AP, you know that we love to talk about when things are positive and increasing, positive and decreasing, and all that kind of jazz. So I want us to look here when they've graphed it. Okay, number one, if you don't know what this would have looked like on rectangular graph, just remember this little 1, that's indicating, or you could even rewrite this, guys. You could even rewrite this as f of x equals 2 sine x, and then that plus 1 at the end. That might make it more clear that that's a shift up 1. We also have an amplitude of 2. So remember that this is amplitude 2. We have shift up 1, all that kind of stuff. And sine starts from the midline and then it goes from there. So if it's been shifted up 1, that midline is at 1, and then it goes up and down and back up. The period has not been messed with on this, and we'll talk about in later problems, we'll talk about how the period can get messed with and how that affects things again. But that all goes back to stuff that we have studied about this a little bit earlier on. Okay, so we're seeing here, it starts at 1, and then we have this amplitude, right? This is A. And so that's a distance of 2, okay? We see it starts here at 1, goes up, then it comes down, and then goes back and finishes out its period by landing at that midline again. Okay, so let's look and see, where is F positive and increasing? Okay, now when we see positive, we mean where is it above the x-axis? Well, it's positive above the x-axis, like that's most of the graph, okay? But it's not increasing that whole time. So I want you to look from the get-go. At the beginning, are we positive? We're above the x-axis, so yes. Are we increasing? Yes, the graph is going up. So from the beginning, we're going to say from 0, we have this little interval until we reach that max point, pi over 2. Okay, now another way to notate this is that we've done this the other way as well, but the other way to notate this would have been from 0 to pi over 2 like this. Okay, so same kind of thing. And then here's the thing though, that's on this graph, it's not the only place where it's both positive and increasing, because I don't know if you notice at the end here, it pops back above the x-axis and it increases. So from 11 pi over 6 to 2 pi, it's increasing again. So we're going to say, and I'm going to write kind of small, but and we're going to say 11 pi over 6. I always have a hard time with writing 11 pi for some reason. When I start writing 11, I always want to turn it into a pi. It's a personal problem, I know, but still, it's always a struggle. I think it's always been like that for me. 11 pi over 6, all right? And then all the way out to 2 pi. Again, the other notation you could have used for this, 11 pi over 6 to 2 pi. Okay, that's the other way you could have noted that. So I know that's little for you, maybe on your screen, but yeah, that's what we're looking at for those. Okay, next, I want you to think about what's going on next. After we reach that maximum value, now this thing starts decreasing. It's still positive because it's above the x-axis, but it begins to decrease. So where it's positive and decreasing, I have to name from here to where it switches to become negative. So that x value here was pi over 2. And then it decreases and is positive until it hits 7 pi over 6. After 7 pi over 6, it becomes negative, so it's not going to fit in this category anymore. Okay, again, you could have done the other notation. AP does not mind, so if you're in AP and you're wondering, like, which one's better, they're fine with either one. Okay, so your other notation would have been this interval notation like that. Okay, negative and increasing. So remember, we hit that x-axis. Now it becomes negative, but it's not negative and increasing right here. It is negative and decreasing. So be careful. It's negative and decreasing. I'm going to jump to the next thing down here. At 7 pi over 6, it decreases until it hits that 3 pi over 2. Oops. There we go. Got to put my inequality in there. And then, again, you can have that other notation if you prefer it. So the 7 pi over 6 to 3 pi over 2 in that interval notation is that way. Okay, and then the last little bit we need is the negative and increasing. So negative and increasing goes up in here, 3 pi over 2 to 11 pi over 6. Okay, again, you can have that other notation if you prefer. Okay, so that's everything, right? So it's just that what you're seeing in the margins over here is the other notation, so you can totally use that too. Okay, so we have shown where are we positive and increasing, where are we negative and decreasing, all that kind of stuff, right? Okay, now, last little thing I'm going to talk about here in this video. I wish I could fit more in the time that I have, but I'm going to run out of time during my conference period here. But the next thing we got to talk about here is when we're going to apply this example 1, but put things back in polar form. Okay, so that's what we're seeing here. Okay, I'm going to give you that one little note. This is saying we're applying example 1 to when input is theta and output is r. Okay, so this is just putting it back in polar, but what I want you to do is compare these. The intervals that we had above correspond with the intervals that you're seeing in here. Okay, they're talking about in this little situation, they said polar coordinate system, we've got this equation, they put it in polar form. They said, as shown in the table above, the labeled points A, B, C, and D correspond to the intervals found in example 1. So that's what this A and B is talking about. They're talking about corresponding with those intervals, okay? So if we were talking about from A to B, they're talking about from 0 to pi over 2, because that was that first little interval. And then B to C, pi over 2 to 7 pi over 6, again, just corresponding with those numbers that we had. Okay, the positive and increasing, positive and decreasing, that is exactly the same as what we had up here in our little table up there. But what I want you to notice, okay, this is the last little piece that we got to compare it to, is we're comparing this, the distance between f of theta and the origin. Is it increasing or is it decreasing, right? And so that's where I was talking about when you're applying it to this graph up here from the beginning, from 0 to pi over 2, from 0, we are increasing in value, increasing in distance from the origin. But then once we get up to pi over 2, we end up hitting our max value and we start decreasing in that distance from the origin. It's getting closer and closer and closer to the origin. So that distance between the graph and the origin is decreasing. Then it hits the origin, it starts going up. So that distance between the origin and the graph starts to increase again till it hits the little max point in here. and then gets closer again. Once it gets down there, it's going to hit the origin and then start leaving it again, so it increases. So what you're seeing as far as these little values on the bottom, that's what it's talking about, is it increasing from the origin. Okay, the last little piece I want to talk about here before I stop this video, and then we'll have to have another one to talk about the rest of this, but the last little thing I want to have here is I want to talk about how that corresponds on the rectangular grid, okay? So when I talked about this thing starting from the get-go, it started to increase from the origin, and then it hit its maximum distance from the origin at the very top, swoops back down, and then it hit the origin at some point. Now, if you watch the Desmos video, you might already start being able to make some of these correlations. But when we are comparing the polar graph in the distance from the origin to a rectangular graph, the origin is kind of represented with the x-axis here. This right here is like the equivalent of that origin, okay? So what I'm going to say here is I'm going to say that this is the polar equivalent of the origin. And it's the whole x-axis. So I want you to see here from the beginning, we start getting up further away from the origin. We reach the highest point away. We dip back down, and then we hit that x-axis at the same place you would have hit the origin on this guy. Then it dips below and it gets further away from that x-axis. That's showing the little loop in here where it's getting away from the origin. It reaches that little maximum point in there, which is the turning point on my little loop. It gets closer to the origin, so this gets closer to the origin, and then it dips back up here, and we can see that little swoopy part in there. Okay, so just trying to compare these, because if you can get a good grasp on how the polar compares to the rectangular, it's going to make things in our section here much, much easier. So that's kind of like a big introduction to being able to do some problems. And so in the next video, we'll actually do some practice problems, and you can see how we can apply all of this. All right. All right, guys, thank you for watching. I will see you in the next video. Bye.